Okay, everybody's here. This is kind of a lot today. We got more to do than we did yesterday. Okay, so I'm not gonna have you write down all those properties of exponents again, because we did before, so you've got them somewhere in your notes. We're just gonna use them and talk about them. What is key on this set of directions is the directions say to simplify. They don't say evaluate, they don't say solve. So when our directions say simplify like these do, you're just looking at as far as you can take it and it stays a whole number. Okay, so if you can't do whatever root and still get a whole number, then you don't do that root. You just leave it in that form. Now, what we're going to do, all of these are in what we would call exponential form because they've got exponents. If they had radicals, you would call that radical form. So since they're all in exponential form, our answers we're going to leave with exponents. So we're not going to yet worry about our power over root and change them and all that. We want to leave our answer the way the problem was presented. Okay? So, numero uno there, 7 to the 1/4 times 7 to the 1/2. What we would remember is that's a multiplication problem, so that's the product property. So we got 7, 7, so we keep 7, and then we add our exponents. So 1/4 plus 1/2, 1/2 is the same as 2/4, so 1/4 plus 2/4 is 3/4. And now if that can simplify, if 7 to the 3/4 can simplify to a whole number, I will, but if not, I'll just leave it like that. So I would say power over root. I know there's not a fourth root of 7, right? So we good with that? That's all you do. That was just using those properties of exponents. So number 2, what do you think we would do first on number 2? It's a completely different one.
Distribute this.
Okay, so we would have power to a power. So this 2 has to go to the 1/2 and this 2 has to go to the 1/3. And when you do that, power to a power, do you add them or multiply them? Nope. Multiply them, there you go. So 6, 2 times 1/2 is just 1, right? So I just got a 6 or a 6 to the first, either way you want to write it, times 2 times 1/3 is 2/3. Okay, so I can't I can't make this do what I did here because 6 and 4 is not the same like 7 and 7 was. So the only way I can go farther is if the 4 to the 2/3 can simplify. Power over root, 4 squared is 16. Does 16 have a perfect cube? No. So that would be my final answer. So the work is not difficult, just using those properties. Right. Okay. Now on the third one down here, that's a -1/5 out here. So we could start it the same way we did up here and distribute it. Is that what you want to do? Or do you want to turn that negative to a positive first?
Turn into a positive.
Okay, so what's the negative exponent rule? What do we do to turn it to a positive? Yep, so we're going to say 1 over 4 to the 5th times 3 to the 5th, all to the positive 1/5 now. So now we'll do what we did here. It's just going to all be under 1. So we'll distribute that 1/5, and that's kind of friendly because 1/5 times 5 is 1, and 1/5 times 5 is 1, right? So I'm just going to have 1 over what?
4.
No? So if you distribute this 1/5 times 5, that gets me 1, so I've got 4 to the first. Here, 1/5 times 5 is 1, so I got 3 to the first. So can I simplify 4 to the first times 3 to the first? To what?
12.
Yeah. Yeah. this page. Okay, so now this little one that's squeezed in here, 5 over 5 to the 1/3, that fraction, that implies division. So we're looking at the quotient property. Quotient property says when you have same base, and we do 5 and 5, you keep that base, but then what do you do with the exponents? Subtract them. So up here on the top, we gotta know that that's an understood 1. So you're looking at 1 minus 1/3, which would be 2/3. Now again, if that'll go to a whole number, you do. If not, you stay. Power over root, we know 5 squared pretty good. That's 25. But is 25 a third root? A perfect cube? No. So that's as far as you go. Alright, lots of cool ways to start on this last one before we switch gears. What do y'all think? What would you try to do first?
Distribute.
Okay, stick the, I mean, we've been doing that pretty constant, and that's not the only right way, but let's stick with what we've been doing. So that would make 2 times 1/3 would make that 42 to the 2/3. Same on the bottom, that 6 times 1/3 would make 6 to the 2/3. Now it's not a quotient rule like the one above it, because the one above it had same base, 5 and 5. This is different, 42 and 6. But that's a division problem, and doesn't 6 go evenly into 42? Can't we divide those coefficients? So, and the reason we can do that though is because they got the same exponent. So 42 to that divided by 6 to that would be 7 to that. Now power over root, 49 is not a perfect cube, so that'd be your final answer. I hope I mean, it's not new, but we didn't do it real long when we wrote down all those properties that day. But this is the kind of stuff you're gonna have for your tomorrow's assignment, some of it. And let me try to clean that page up. I wrote over on this problem I didn't want to. Try to clean this up for the other classes. Okay, bigger eraser now.
You forgot to add the squared back to the last time.
Thank you. Let me get that 1/6 and I'll go put it. Thank you. That would have made me confused. There we go. Alrighty, let's clean these up. Okey-dokey, artichoke. Okay, so number 1 up there, I got the cube root of 12 times the cube root of 18. So the first page, everything was in exponential form. Everything had exponents. This page I've given us 2 that are in radical form. They both got the, remember I told you that symbol's called the radical, the cube root, the fourth root, they both got the radical on them. So it's not any different for us. On the top one we can, that's a multiplication problem, that little dot there. So you've got to check and ask yourself, can I multiply those? And the answer here is yes, because they're both cube roots. If you got a cube root times a cube root, you keep that cube root, multiply what's underneath. If one of these had been a fourth root and a cube root, there would be nothing you could do. But cube root times a cube root, yes ma'am, we can do that. We'll get a cube root. What's 12 times 18? 216. Now, I remember that number from yesterday. I think that's a perfect cube. If it is, we'll simplify it. So on your calculator, hit math 4 and type in 216, and I think that's a perfect cube. Okay, so we get 6 on that. Now, if it had not been a whole number, we would have just stopped here. So we got to check them and see, but okay, so based on that, we ought to know what to do with number 2 down here. It's a division problem, so you got to ask yourself, can I divide? Yes, because they're both the same root. Fourth root divided by fourth root, you keep that root. So what's 80 divided by 5? 16 it is. Now we stop if it's not a perfect fourth, but I believe 16 is a perfect 4. What's the fourth root of 16? Hit math 5 until 2. Now, I need to put something with this 2, and we talked about it yesterday. Okay, because we did an even root, we got to throw the plus minus sign. Up here on the first one, it was an odd root, so we just kept it the sign that it was. Even root, plus minus sign. Good job. Hey, Christian. Man, this is good stuff.
Christian probably would have started writing down something like that.
Yep. Okay, so now what we're going to look at, let me go ahead and we'll just do one at a time on this. What we're going to look at now is, the directions say to write the radical in simplest form. So they want us to break that down and our answer still be a radical. So first thing I would do, just to make sure, is I would see if that is if I get a whole number with that. Is that a perfect cube? So I would hit math 4 and type in 135. If we do, we hit the jackpot.
Nope.
No, we didn't hit the jackpot. So now what we've got to do, and we did this with square roots before, what we got to do is find the biggest perfect cube that will go evenly into 135 so that we can set up our wiffle ball game. Okay, so I'm just going to start making a little list. I don't know them as good as I do the squares. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed we've seen is 216. So that list is long enough to get 135. So now we go to the biggest one that's smaller than it and start seeing if they'll go evenly. So will 125 go evenly into 135? No. Hit 135 divided by 125, you don't get a whole number. Will 64 go evenly into 135? No, a 4 can't go into a 5. Will 27 go evenly into 135? Okay, how many times, Holly? So 5 times 27. So we're going to say this is the same as the cube root of 27 times 5. And now just like we did with square roots, the perfect cube will get to come out and play, and the other one has to stay in the house. So the cube root of 27 is 3. So we're going to bring a 3 out to our wiffle ball game. So we got 3 cube root, and then 5 will have to stay in. So that would be your final answer. Okay, let's look at this one. This one's a little bit more challenging. 5th root of 7 over the 5th root of 8. Okay, so the directions are the same. Write the expression in simplest form. And you're thinking, well, they're both 5th roots, so I can divide them, but 7 divided by 8 doesn't go evenly. So 7 over 8 is reduced as far as it will go. So it is in simplest form, but just like with square roots, we're not allowed to leave a 5th root on the bottom. You can't leave a radical on the bottom. So we got to figure out what we can do to cancel this 5th root out. Now, it was real easy when we did square roots, because you could multiply it by itself, and that's a square, so that would cancel a square root out. But we've got to find a perfect 5 that 8 will go into to use to cancel this out. So let's make a list of some perfect 5s. Why 5s? Because it's a 5th root, right? So 1 to the 5th is 1. 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay, that's enough. I can stop already. Because 8 does go into 32, right? 8 times 4 would make 32. So if I could multiply this by the 5th root of 4, what would I have to do to this? If I multiply the bottom by the 5th root of 4,
You have to do
I have to do the top. Do you know why I'm doing 5th root of 4? That would make a 5th root of 32, which is a perfect fifth, right? So I can cancel that radical out. So I'm going to say times the 5th root of 4 times the 5th root of 4. So on the top, that'd be the 5th root of 7 times 4, which is 28. On the bottom, that would be the 5th root of 8 times 4, which is 32. But look, that reduces to 2. So we've got the 5th root of 28 over 2. Now, the only way you would go farther here is if you had a perfect 5 that would go evenly into 28. But the smallest one other than 1 is 32, and that doesn't go into 28, so this would be your final answer. Those, in my opinion, are sometimes the trickiest. Alrighty. Y'all getting some good notes? Alright. I'm going to give you the 4th root of 10. I think this phase of the notes is easier than the last one. Plus 7 4th roots of 10. Okay, so the directions here say simplify the expression. This type of problem always freaks people out. But if you think, this is an addition, so we changed gears a little bit. If you think of those 4th root of 10s as an object or a variable, it's the easiest kind of problem there is. Because I could say, now you make this 4th root of 10 be a guitar. So I got 1 guitar plus 7 guitars. Right? So 1 of those and 7 of those gives me 8 of those. And that's it. That's your answer. Now, we got to do that because 4th root of 10, 4th root of 10 exactly the same. So that's like 1 apple and 7 apples gave you 8 apples. So easy stuff on that. That's what looks difficult, but it's really nothing but a thing. Okay, so same deal here. That looks pretty overwhelming, but you got 2 of something plus 10 of something. So wouldn't that just make 12 of something? That's it. Because 8 to the 1/5 is not going to simplify, because that means 1/5 power over root. That means the 5th root of 8, and that's not a perfect 5, so as far as that'll go. Okay, but now what if you've seen those 2 problems and all of a sudden you got this one? Okay, that's not a guitar and a guitar anymore, is it? Those are different. But you got to see if you can break them down. Okay, you know you're not going to break this one down, right? This cube root of 2 is not, that's staying in the house and doing chores all day long. But what about 54? I almost just said the answer. Is there a perfect cube that will go evenly into 54?
8.
54 divided by 8 is what?
My brain is not working today.
So it didn't?
No.
I know this one will. How many times will 27 go into 54? What's 54 divided by 27? 2. So this is the same as the cube root of 27 times 2. And then the cube root of 27, we just found out over here was 3. So I'll bring a 3 out to play wiffle ball. That 2 has to stay in the house. And isn't that convenient? Because that's what's in the house over there on the other side of the minus sign. So now we got our guitar minus our guitar, right? 3 of them minus 1 of them is 2 of them. I like it. Now, we did all of those with only numbers, so guess what happens now? Variables! Woo! Things like it's about time we get to the fun stuff.
Mm-hmm.
Alright. So we got the cube root of 64y to the 6th, and it says to simplify the expression. So let's attack our plain old numbers first, because we just practiced with those and we're good with those. You got a calculator, if you don't know, is 64 a perfect cube? Math 4?
Yes.
It is? Okay, so what times itself 3 times is 64?
4.
So I'm going to bring a 4 out to play. Nothing has to stay in the house with that 64. So we bring a 4 out. So we've got 4 cube roots of y to the 6th. Now, is y to the 6th the perfect cube? Yes. Okay, and it's easier than you think on letters because you can just divide. So you say you got a 6 here divided by 3. So that means I'm going to bring a y squared out to play. Now here's how it works for real. I got a perfect cube, so how many cubes can I write my 6 in? That's weird to say. Is this the same as y to the 6th? That's what I was hinting at. Because you would add 3 plus 3, so that's the same as y to the 6th. So the cube root of y cubed is y. And then you got another one. So a y and a y makes a y squared, which is what you got with your division there. Okay? So we have nobody left to do chores. This is the first time in a while everybody's getting to play in the wiffle ball game.
I think that's the first time ever that we haven't had a record. I could be wrong there.
Okay, I'm going to skip those two and get a tougher one. 14 xy to the 1/3 over 2x to the 3/4 z to the -6. Okay. So nobody's going to panic here. We've obviously got quotient property going to be happening. And on quotient property, we subtract exponents. But before you do that, go ahead and just work left to right and do your coefficient division. So you got a 14 divided by 2 to start with. That's going to get us a 7. Okay, we all right? Now let's go look at our x's. And on our x's, it's division like I just said. So we're just going to subtract our coefficients. Rewind. What are we going to subtract? Exponents. Mm-hmm. So that's an understood 1 on the top. So what's 1 minus 3/4? 1/4. Okay, now I go to my y next. I got a y on top, but not one on bottom. So I don't have anything to do with it. So I'm just going to keep it like it is. So I've got everything on the top. Uh-oh, I haven't messed with this z to the -6 on the bottom yet. But there's nothing to divide it with, but I can't leave a negative exponent. So what's it going to do?
Would we put it up top?
You always, very good. Usually we say put it on bottom and make it positive, but if it's already on bottom, you put it on top and make it positive. So that's your final answer. Looks ugly, but 14 divided by 2 was the hardest math you did there, right? Just looks ugly.
Yeah, I was confused when it was 14xy. I was like,
That did not sit well with me.
Alright, let's do one more. Think we can handle one more? We've done a lot today, haven't we?
Let's see, that's one. This will be our 15th.
This will be the biggie. 12 cube root of 2z to the 5th minus z cube root of 54z squared. The directions say to perform the indicated operation. Okay, so this isn't, we don't get to do this like my guitar problem, because 2z to the 5th is not the same as 54z squared. But, so what we are assuming is that at some point we will get them to be the same, so they must simplify somehow. Okay, so let's try to see if we can simplify these. 2 cube root of 2 is not going to get to come out. Cube root of 2 is going to stay in the house and do chores all day long. But I bet with z to the 5th, some of those z's can come out. So let's just break that down. Since it's a cube root, I wonder if I can say that's the same as the cube root of z cubed times z squared. Is z to the 5th the same as z cubed times z squared? Because 3 plus 2 makes 5. Why did I want to do that? Because now cube root and cube, I can bring the z out. Right? So I get to bring a z out, and then that z squared will have to stay in there with the 2. And then we already had a 12 out, so don't forget to drop that down. Okay, so we are closer to looking like this other side now because our z's are both squares, but this one's got a 54 in it. We worked with the 54 earlier. This is a perfect cube. What was the biggest cube that would go evenly into 54?
27.
So it's going to be 27 times 2 times z squared. And the cube root of 27 is 3. That'll have to stay, and that'll have to stay. Okay, and there was already a z out there. I put my 3 too close on. It's going to be weird putting my z in front, but it's okay. Now, other than I wrote z3 instead of 3z, do I have like terms? Can I say these are the same guitar or the same apple?
Yeah.
Cube root of 2z squared, cube root of 2z squared. So 12z of them minus 3z of them. What's 12 minus 3?
9.
So I got 9z times the cube root of 2z squared. Hold on just a second. Let me mark some things in my book so I know to do with the other classes what I did with y'all. Because I jumped around a little bit. Didn't do. Let me just go back. Are y'all done writing that? Let me go backwards for a second.
Is that it?
14. Yeah, but just hold on a second. I got just a couple things to tell you. But yeah, that's it. We did that one. And that one. I'm changing my plans. 64, that one. Where's that at? That one, that, so we did all 3 of those. Okay, and then, about to lose my glasses. 7, 8, we did that one. I don't know if we did that one. Yeah, we did do that one. Alright, I think that'll be good enough. Let me make sure. Yeah. Come on, page. Cube root of 12. Where did we do that one? Right there. Got it. Okay, so tomorrow's stuff, and I'll post it probably before I go get on the bus today. But tomorrow's stuff, it's a worksheet that has, I think it has 25 problems on it altogether, but you're only going to do the evens, so you're only going to have 12 to do, and it's over the stuff we did today. So you got your notes, you got your property of exponent rules, show your work, attach it, all that good stuff. Okay, doke? We good? Alrighty.